Hello, myself Sharin. This video is part of the series Architecting Machine Learning Systems. The topic in discussion today is Explainable AI. We will be discussing some important concepts, techniques, and tools related to explainable AI systems in today's video. AI systems often make decisions in ways that most people don't understand. Although these systems, especially those using deep learning, are very accurate, it's hard to see how they come up with their recommendations. It's important for us to know how these AI decisions are made so we can trust them. We need machine learning models that work well, explain their decisions clearly, and show us how they operate. Explainable AI is a key area of research that helps make AI more understandable. This helps us use AI systems effectively while making sure they stay accurate. Explainable AI refers to the methods and techniques in the field of AI that makes the results of the solution understandable by humans. Unlike traditional black box AI models, XAI provides insights into decision-making process, making it transparent, understandable, and trustable. IBM's Watson for Oncology is a tool that's been designed to help doctors with cancer treatments. It uses AI to look at patient data and then suggest what kind of treatment might be the best. There's this question though: can doctors and patients really trust an AI system if they are not sure why it's recommending certain treatments? They addressed this issue by making the predictions transparent. It doesn't just make suggestions without any backup. Watson provides reasoning for its recommendation, citing medical literature and patient data, making its decision-making process transparent. So it's not just about gaining the trust of doctors. It's also useful as an educational resource, helping them understand complex treatment plans better. In the finance sector, companies like Zest Finance use AI for credit scoring. However, initially, their models faced challenges due to the lack of explainability. People were not in a position to know why their loan applications were rejected. Without understanding the rationale behind a credit decision, applicants will be having a hard time challenging or appealing a decision, right? Such Finance later integrated XAI to provide clear explanations for credit denials, aligning with the regulatory requirements and building customer trust. This shift towards transparency helped in regulatory compliance and enhanced customer relationships. Tesla's autopilot AI system, they faced scrutiny after several incidents, raising concerns about its decision-making in complex driving scenarios. The incidents highlight the need for explainability in automated vehicle systems for both user understanding and safety. They, along with other automotive companies, are now focusing on making AI decisions in autonomous driving more interpretable and user-friendly. Amazon, they use AI for product recommendations, which is a key driver for its sales. To make these recommendations more user-friendly, Amazon incorporates explanations in the form of labels, like customers who bought this item also bought, making the AI's logic transparent. This level of explainability has not only improved customer experience, but also increased sales by making recommendations more persuasive and relevant. In sectors like healthcare or finance, where decisions significantly impact human lives, trust in AI systems is paramount. And with regulations like GDPR mandating transparency in automated decisions, XAI becomes a legal requirement in many scenarios. From a development perspective, understanding AI decision paths allows architects and developers to refine models more effectively. Model interpretability involves designing models whose internal workings are either inherently understandable or can be made understandable. A post hoc explanation are the techniques that can explain AI decisions after the fact. Let's discuss some of the techniques for making machine learning systems understandable. Local interpretable model-agnostic explanations, developed in 2016, has been widely used to explain predictions from complex black box models in fields like finance and healthcare. Imagine having a complex AI model like a deep neural network. LIME helps by creating simpler local model around a specific prediction to explain why the AI made that decision. It's like zooming in on a small part of a complex picture to understand what's happening in that section. For instance, in a loan approval AI system, LIME could explain why a loan was denied by highlighting key factors like low credit score or high debt to income ratio in a user-friendly manner. This helps in not just understanding, but also potentially addressing these issues. Capital One uses LIME to understand credit decision models. By applying LIME, they can explain specific credit decisions to customers, such as why a credit card application was declined based on factors like payment history or debt levels. Even though it provides local explanations for individual predictions, which are easy to understand, being local in nature, LIME's explanations are limited to specific instances and may not represent the model's overall behavior. LIME is available as an open source Python library and can be applied to any classification models. SHapley Additive Explanations. SHAP is based on game theory and helps in quantifying the contribution of each feature to the final prediction. If we consider features as players and game as a machine learning model, it's like assigning a score to each feature in a model to understand their role in the model's outcome. In a healthcare setting, if an AI model predicts a high risk of a certain disease, SHAP can show which symptoms or patient history factors most influence this prediction, helping doctors in making informed decisions. PayPal employs SHAP to interpret their machine learning models that detect fraudulent transactions. SHAP helps them understand which transaction characteristics most contribute to a fraud alert, aiding in refining their fraud detection algorithms. While SHAP offers global interpretability and is model agnostic, SHAP can be computationally intensive for models with large number of features. SHAP is available as an open source Python package and can be used in many types of ML models. Integrated gradients. Integrated gradients, widely adopted in image and text classification tasks, is especially useful for deep learning models. It highlights how much each input feature contributes to the final decision, creating a gradient or spectrum of influence for each feature. For an image recognition model, integrated gradients can indicate which parts of an image, like edges, shapes, colors, were most influential in identifying an object, enhancing our understanding of the model's visual interpretation process. Google Brain uses integrated gradients for its image recognition models, particularly in medical imaging, to understand which aspects of an image lead to a specific diagnosis, enhancing the reliability and trustworthiness of their AI diagnostics. While provides detailed feature attribution, especially useful for models with high dimensional input like images, its reliance on gradient information makes it less suitable for non-differentiable models such as decision trees, random forest, other rule-based systems, canons, etc. TensorFlow supports integrated gradients. Counterfactual explanations. Counterfactual explanations are being increasingly used in customer-facing applications and regulatory compliance. Counterfactual explanations provide insights into what minimal changes would lead to a different prediction. It's like exploring alternate scenarios to understand what could have led to a different outcome. In a credit scoring model, counterfactuals can show how small changes, such as a slight increase in income or reduction in existing debt, could flip a loan rejection to an approval, guiding applicants on how to improve their creditworthiness. Monzo, a digital bank, uses counterfactual explanations to provide insights into their credit scoring decisions. By showing customers how altering their financial behaviors could lead to different credit outcomes, they offer more transparent and actionable financial advice. There are various Python libraries which can offer support for generating counterfactual explanations based on your requirements. Activation maximization. Activation maximization is used predominantly in neural network interpretations, particularly in image recognition tasks. In neural networks, this technique finds the input that maximizes the response of a particular neuron or layer. It's like discovering what specific features or patterns an AI model is most responsive to. For instance, in a facial recognition system, this method can reveal what features like eyes, nose, etc. the model focus on most, providing insights into its recognition process. DeepMind uses activation maximization in its neural networks to understand and visualize how different network layers respond to various inputs, particularly in their AI research for games and simulations. While it helps visualize what features a neural network layer is focusing on, the interpretations can sometimes be abstract and not easily comprehensible. Deep visualization toolboxes in deep learning frameworks like Keras offer activation and maximization functionalities. Global surrogate models. Global surrogate models are used to approximate complex models with the simpler interpretable ones. It is widely used in industries where model transparency is crucial. These models simplify a complex AI model into a more understandable form. It's like translating a complex scientific theory into layman terms. A global surrogate model can make a sophisticated customer recommendation system more interpretable by approximating it with a decision tree, thus providing a clear rule-based insights into its recommendation logic. IBM uses global surrogate models to interpret their Watson AI solutions. By approximating complex models with decision trees, they provide their clients with more understandable insights into how Watson arrived at its conclusions. Even though global surrogate models provides an overall understanding of the model's behavior, the surrogate model's accuracy might not always match the original model. Simple ML models in scikit-learn can be used as global surrogates for more complex models. Feature importance measures. Fundamental in ML, these measures are critical for understanding which features most influence predictions. This is about evaluating which features in your model are most influential. It's similar to figuring out which ingredients in a recipe are most crucial to the dish flavor. In real estate price prediction models, feature importance measures can identify key factors affecting property prices, such as location, size, and amenities, aiding real estate agents and buyers in understanding market dynamics. Airbnb uses feature importance measures to understand factors influencing their rental pricing models. This helps in identifying key drivers like location, property type, and seasonality in their dynamic pricing algorithms. This helps in model debugging and identifying key drivers in predictions. But please note that feature importance measures might not capture the interaction effects between features. Libraries like ELA5 and scikit-learn provide functionalities for feature importance evaluation. Partial dependence plots, PDPs. PDPs are standard tools for interpreting the effects of features on predictions, particularly in economics and social sciences. PDP shows the relationship between a specific feature and the predicted outcome, keeping other features constant. It's like isolating a variable in an experiment to see its direct effect. In agricultural AI models, a PDP for a factor like soil acidity can reveal how it affects crop yield independently, helping farmers optimize growing conditions. Uber uses PDPs to analyze how different factors affect ride demand predictions. By understanding the impact of variables like time of day and weather conditions, they can optimize their ride allocation and pricing strategies. PDPs offers clear visualization of the marginal effect of features, but they assume features are independent and can be misleading if there is a strong interaction between features. The PDP box Python library and scikit-learn offer support for creating PDPs. AI Fairness 360. AI Fairness 360 is developed by IBM, which is a comprehensive toolkit aimed at ensuring AI fairness, widely used in sectors like banking and human resources. This is a comprehensive toolkit for detecting and mitigating bias in AI models. It's like having a fairness auditor who checks and corrects for any unfair bias in your AI system. For example, for HR recruitment AI tools, AIF 360 can ensure that the model doesn't favor or discriminate against any candidate based on gender, ethnicity, or other sensitive attributes. HSBC has utilized AIF 360 to ensure fairness in their credit scoring algorithms. The toolkit helps them identify and mitigate biases, ensuring that loan approvals do not discriminate against certain groups or customers. A Fairness 360 offers metrics and algorithms to detect and mitigate bias, and it's very important to have careful implementation to ensure appropriate bias mitigation techniques are used. AIF 360 is available as an open source Python toolkit. What If tool. What If tool was developed by Google. This tool is used for model comparison and understanding model behavior under different scenarios. This tool allows you to take input data and see how these changes affect your model's predictions. It's like a simulator for AI models where you can experiment with different scenarios. In marketing AI models, this tool can help understand how changes in customer demographics or behavior might affect sales predictions, aiding in strategic planning. Twitter uses the What If tool to analyze and understand their tweet recommendation algorithms. This tool helps them investigate the model's performance across different user demographics, ensuring that their content curation algorithms perform equitably. What If tool facilitates easy exploration of model predictions for different input configurations. This tool can be integrated with TensorBot, and it can be used with the models built using TensorFlow. By integrating these techniques and tools into your AI systems, you can make your models not only more transparent and understandable, but also more trustworthy and effective. Each tool serves a unique purpose and can be instrumental in demystifying the complex workings of AI models, making them accessible and actionable for everyone involved. Explainable AI is not just a trend, but a necessity in the most modern landscape of AI and ML. Architects designing ML systems must prioritize explainability to build trust, comply with regulations, and create systems that are fair and understandable. Okay, that's it for today. We'll see you again. Stay tuned. Bye for now. Thank you.